In this short video, we're going to explore computer number systems, specifically decimal, binary, and hexadecimal, and how to switch back and forth between each of the number systems. Let's start with what we know. We start with the base 10 numbers that we're all familiar with, 0, 1, 2, all the way to 9. These, again, are the symbols for base 10. You'll notice the number 10 is not part of the base 10 numbering system because 10 is composed of two symbols. It's composed of a 1 and a 0. When we talk about the anatomy of a number, there are two things to keep in mind. One is the symbols, the other is the places. For example, 10 squared we know as the hundreds, 10 to the first power we know as the tens, 10 to the 0th power we know as the ones. Then there's a decimal point, and we can go the other direction. 10 to the negative 1 is tenths, and 10 to the negative 2 is hundredths. And we can continue that in either direction as we desire. One more time, because this is so very important. When we talk about a number, there are two things we're talking about. We're talking about the symbols that are used to make that number, and we're talking about the place value. For example, if we were presented with the number 782 base 10, we can write this number in expanded form. So that's expanded form. So first, we see the symbol 7. That symbol has a place value of 10 squared because we're dealing with 7 hundredths. We can then add 8 tens, and finally we can add 2 ones. So 7 hundredths, 8 tens, and 2 ones. One more time, symbol and place value. And let's not forget this term, expanded form, because it will be very important to us in the next steps. This concept of symbol is a little bit abstract, and I think it's helpful if we look at a visual aid to help us explore what its meaning is. One way to think about symbols is to think about color. For instance, you could talk about numbering systems as M&Ms. That's not good. We seem to be missing a certain color. Let's get another bag. You could talk about numbering systems as colors. There we go. That's the one I was looking for right there. Okay. Now, in this number system, we're going to use color as a symbol. So let's start with brown as the first symbol, red, orange, yellow, green, and blue. So our symbols are brown, red, orange, yellow, green, and blue. We'll abbreviate that as B, R, O, yellow, or Y for yellow, G, and A for blue. At this point, we need to figure out what base we are using, and one way to answer that is to figure out how many symbols there are. In this case, there are 6 symbols, so this is going to be a base 6 numbering system. Remember up here when we talked about base 10, there were 10 symbols. We went from 0 to 9. now we're in base 6, and we go from symbols brown to blue. At this point, we need to ask a question, and that is, how precisely do we count in this base M&M that we just devised? Well, it looks something like this. We start with our base. In this case, base M&M is base 6, but with color as a symbol. And in this column, we'll write our decimal number. We'll start very simply with decimal 0, which is represented by a single brown candy. Decimal 1 with a red. Decimal 2, orange. 3, yellow. 4, green. And 5 as blue. So far, no problems. But we're out of symbols, aren't we? What we need to do is the same thing we do for our base 10 numbers. For example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, we've used all of our symbols, so what comes next? Well, the answer is you use 2 symbols. But remember what I stressed so much before? I said there's symbols and there's place. So when we were using this column, these were all the ones place. When we run out of symbols, we just add another place to the left and keep on counting. And that's exactly what we do in this column. So once we reach this point here, 6 would be red and brown. 7 would be red, red. 8 would be red, orange, and we just continue on with red, yellow, red, green, and red, blue. You'll notice we repeated all our symbols here, all 6 of them. And in our ones column, we've once again repeated all of our symbols. So the next one would be orange, brown, orange, red, orange, orange. For decimal, let's see, that would be 12, 13, and 14. And of course, we could continue this on forever if we like. Now that we've seen the pattern, let's see if we can apply it. Suppose we have this as our code. We have 3 candies. All of them are blue. So we've got blue, and we've got blue. What number does that represent? Well, remember there was 2 components. There was a place component and there was a symbol component. To answer that question, we have to go back to our original table, and we make a statement that brown is 0, red is 1, 2, 3, 4, 5. What we just did is we took our symbols, which were originally colors, and we've given them numbers that are something more familiar to us. Keeping in mind that we're dealing with base 6, we go back here and we try to write this in expanded form. Since it's base 6, the first column is 6 to the 0 power. This next column is 6 to the first power, and this one is 6 to the second power. We would recognize this as the ones. We would recognize this as the 6th column, and this would be the 36th column. In expanded form then, we'd go back here and we'd say blue is 5, so that would be 5 times 6 squared plus 5 times 6 to the first power plus 5 times 6 to the 0 power. Once we get this far, we're in a good position to do a conversion over into decimal form. So we could say that this is 180 plus 30 plus 5. So 555 base 6 is equal to 215 base 10. Just to recap, we started out here. There were 3 columns. Each column contained a particular symbol, in this case blue, and associated with each column was a particular place. The column on the right is the ones place, then the 6s, and then the 36s. Keeping in mind that it's always base to the 0, base to the 1, base to the second power. Once we understand that relationship, we can take a number from any base and convert it over to decimal with very little trouble. For example, if you have the number 2101 base 3, we want to convert that to decimal. It's base 3, so we recognize this as having symbols 0, 1, and 2. So it has 3 symbols. As far as places are concerned, this 1 is in the ones column. So that's 3 to the 0 power. This is the 3's column. That's 3 to the 1. This is the 9's column, 3 squared. And this is the 27's column, so 3 cubed. If we were to write this number in expanded form, that would be 2 by 3 cubed plus 1 by 3 squared plus 0. We don't care what it's multiplied against, but we'll write it anyway. So that's 0 times 3 to the first power. From there, we can say that we have 2 times 27, which is 54, plus 9, plus 0, plus 1, and finally solving for the whole thing, that's 2101 base 3 is equal to 64 base 10. Here's another example. This time we're going to go base 2, so 1010 base 2 to decimal. Our symbols are 0 and 1. Base 2 has 2 symbols. Our places are 2 to the 0, 2 to the 1, 2 squared, and 2 cubed. So symbols and places. In expanded form, we take this first digit, and it's 1 by 2 cubed, plus 0 by 2 squared, plus 1 by 2, plus 0 by 1. And converting that to decimal, that would be 8 plus 0 plus 2 plus 0, meaning that 1010 base 2 is equal to 10 base 10. If we wanted to write down some general rules, we could say these are the steps. Our first goal is to establish places. Our next rule was to write it in expanded form. And from there, we simplify. Before we move on, we should mention that these were the steps to go from an arbitrary base, we'll call that base x, to decimal. Now, if we can do that, we can certainly go in the other direction. So what if we want to convert 10 base 10 to binary? Our opening move is to take care of the places. So 2 to the 0, 2 to the first power, 2 squared, 2 cubed. And I'm going to write the decimal equivalents down. So that's the 1s, the 2s, the 4s, and the 8s. Now, take the number of interest. That would be this number here. We're going to write it like so. Now we're going to perform a series of subtractions. So we have the number 10, and we ask ourselves, how many times does 8 go into that number? And the answer is, well, it goes in 1 time. So we write a 1 here. And the remainder of that operation is 2. How many times does 4, which is the next number, go into that? The answer is it doesn't. So that's 0. How many times does 2 go into this? 2 goes in once with a remainder of 0. So we put a 1 there. And then how many times does 1 go into 0? The answer is it doesn't. And that's it. We can say that 10 base 10 is equal to 1010 base 2. Right, we just take that number right there as it exists. I believe your textbook author calls this the addition method. That wasn't so bad. Let's try another example. So this time we want to take the number 10, base 10, and we want to convert that to base M&M, which we said was a base 6. Our opening move is to establish the places. 6 to the 0, 6, 1, 6 squared. So that's the 1's place, the 6's place, and the 36's place. As before, we take this number and we move it down here, and we ask a series of questions. How many times will 36 go into 10? The answer is it doesn't. So that's a 0 here. How many times will 6 go into 10? The answer is 1. So we put a 1 there. The remainder is 4. How many times will 1 go into 4? The answer is 4 times. Which tells us that 10 base 10 is equal to 14 base 6. If you go back and look at the codes, I believe that was red and green. Let's do this one more time for good measure. We'll take the number 215 base 10. We want to convert that to base 5. Places, so the 1's, the 5's, the 25's, the 125's, that's 1, 5's, 25's, and 125's. As before, we take that number, we move it down here, so 215. How many times does 125 go into 215? The answer is 1, with a remainder of 90. How many times does 25 go into 90? The answer is 3, and that gives us a remainder of 15. How about 5? How many times does 5 go into 15? The answer is 3, and we're left with nothing, so we'll just put a 0 there. Which means our number 215 base 10 is equal to 1330 base 5. Well, very good. So far, we've seen how to go from an arbitrary base, so base x, to decimal. And we've seen how to go from decimal to some arbitrary base x. In the computer world, this base x usually takes on a few forms. It'll take on binary, which is base 2. It'll take on octal occasionally, which is base 8. More common is hexadecimal, which is base 16. Knowing this, there's a few shortcuts you should be aware of. One of them is called the divide by 2 method. For example, if you have the number 25 base 10 and you want to convert that to binary, you can perform a series of divisions by 2. It looks something like this. We start with the number 25. We divide it by 2. The answer is 12 with a remainder of 1. Now we take 12. We divide it by 2. We get 6 with a remainder of 0. Take the number 6, divide it by 2. That's 3. Remainder 0. Divide 3 by 2. That's 1. Remainder 1. Now divide 1 by 2. That's 0. Remainder 1. From here, we start at the bottom and we collect all of our bits. So we say 25 base 10 is equal to 1, 1, 0, 0, 1 base 2. As for your opening move, remember this piece right here was 25 divided by 2 is equal to 12, remainder 1. Be careful with this method. There is a stumbling point. You have to remember to collect your bits from the bottom. One way to remember what you're doing here is to consider what this particular bit means. This bit will tell you if the number is odd or even. 25 divided by 2 is going to be odd, so this here is a 1. Had we used the number 24, this would have been a 0, indicating an even number. Here's another shortcut you should know. We'll start with a 3x5 note card, fold it, and then fold it again, and again. So that when you're done, you have something that looks like this. And now we will do some writing. Onto the paper, you'll write numbers like this: 0, 1, 2, 3. There's the first fold. 4, 5, 6, 7. Second fold. 8, 9, 10, 11. Fold. And 12, 13, 14, 15. So that looks like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, 14, 15, like so. Next, you're going to write the binary numbers down. 0, that's 0, 0, 0, 0. 0, 0, 0, 1. And at this point, we're going to watch for patterns. I told you that last bit, the least significant bit, this one right here, was the sign bit. So 2 is even, 3 is odd, 4 even, 5 odd. And you continue that pattern like so. Now we come here and remember the places. So this is the 1's place, and this is the 2's place. So the number 2 would be represented as 0, 0, 1, 0. The number 3 would be 0, 0, 1, 1. So you could read that as 2 plus 1 is equal to 3. And I think you see the pattern here. So the 1's column alternated between 0 and 1. The 2's column alternates 2 zeros, 2 1's. So it would be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Next, we deal with the 4's column. So there's the number 4 right there. So that's a 0. 5 would be 4 plus 1. 6 would be 4 plus 2. And 7 would be 4 plus 2 plus 1. Which brings us to the 8's. And I think, again, you see the pattern. In the 4's column, we have 4 zeros, then 4 1's. We're going to have, oops, that's a mistake there. We're going to have 4 zeros and 4 1's. Back to the 8's. I think you see it here. There's going to be 8 zeros, and then there's going to be 8 1's. In this last column, we can put in the hexadecimal values. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So everything was the same as before, but we need more symbols because hexadecimal, did we write that down? Hexadecimal was base 16. So there's 16 symbols that we have to work on. We've already used our symbols 0 through 9. We may as well continue using letters. So A, B, C, D, E, and F. To see how this works, consider the number 12. So 12 base 10 could be represented as 1100 in binary or as the symbol C in hex. Once again, this was decimal. This column was, what did we say? Binary. And this column was hex. Be sure to transfer that to a note card. When you're done, you should have something that looks like this. And this will be most useful on your quizzes and exams because there's a very nice relationship between binary and hexadecimal. And it goes something like this. Suppose you have this number 100110110 base 2, and you want to convert that to hexadecimal. This is a very easy operation because all you need to do is group your numbers like so. So you chunk them into groups of 4 with the understanding that there are leading zeros out here. And now you get your converter card and you look that up and you say, well, this is a 1. Now you look at the next number, 0011, that's a 3, and 0110 is a 6. So we can say 100110110 base 2 is equal to 136 base 16. And of course, you can go the other way by just expanding these numbers out. So you can see that hexadecimal is a very nice way of representing a binary number without carrying all those digits. I think you'll agree that 136 is much easier than saying 100110110. As we finish up here, know that there are online tools to perform this change of base operation for you. However, for our exams and quizzes, I would like you to perform the operations that we've just gone over here. Specifically, the concept of symbol and place. If you know those concepts, you can perform any change of base operation.